Today's lesson is about using definite integrals to find the area under a curve and some of the applications involved in that. So what we have to do is work from an indefinite integral, but what we want to look at is what we are trying to accomplish. So if I have some curve and I'm looking from point A to point B under this curve, I need a way to be able to calculate all of this area underneath this curve, okay? And one way we can do it is a process of estimation where we start out at a particular height and we just come over from that height. Notice each one of these is going to be the same, okay? So we're building an estimation of the area underneath this curve. Now, I hope as I'm doing this, you're seeing a small problem develop. Okay? Notice when I'm doing this, all of these areas right here are not being calculated for the total area, because all I can calculate here is the area of a rectangle, okay? This here is going to be known as the change in x, because that's what we're doing. We're moving along the x-axis, right? And a value here would simply be the height of that rectangle, okay? So if this point here functions as x1, this would be x2, x3, x4, x5, x6. The height of this side of the rectangle would simply be this x value plugged into my function, right? Because this would give me the y value if I plug in that x. So the area of this triangle would simply be the change in x times the height. And then I could do that for each one of those triangles, okay? But see what's happening? This is only an estimate because I'm missing all of those particular calculations because I have no way of looking at this. I can't call it a true triangle because it's an arc, right? So one way to improve upon that is to take my function across the same change in x total, right? But if I looked at this and see how wide my x's are, if I were to go through and do a much smaller version of my change in x, right? I'm actually going to get a much better estimation of what's going on, because in this case, let's say I've divided this up into 4 sections. I'm much closer to the curve, right? I'm losing less of an area here. So I'm getting a better idea by increasing the number of samples that I take, okay? Well, this here is known as a Riemann sum, okay? When I add up all of these particular rectangles, okay? So I would do this all the way up to, in this case, the change in x times f of x to the 6th, right? So this here, if I were to do that, would allow me to get this estimate of area. Again, estimate, okay? If I make the change in x smaller, I'm going to have many, many more individual areas to add up, but I'm going to get much, much closer to that actual area underneath that curve, okay? And, you know, that truly is what I'm looking for. Every bit of the area underneath the curve, okay? So I can do this. This is known as, like I said, the Riemann sum. But what I need to do is keep making this change in x smaller and smaller and smaller, all right? Well, when I do that, I now have what is known as the definite integral, okay? So I work from a to b, and I take the integral of the function, and the function is this curve, okay? And that's going to give me something that's going to look like this. So when I see the capital F, I know it's the integral of that function. And then you will see this bar out here that's telling me what my limits are, okay? So A here is the lower limit. And then that, of course, would make B the upper limit, okay? And what I'm really doing here now is I'm going to break this out into the following equation. So I'm going to take f of x from A to B, and I'm going to break that out into the value of B in my integral minus the value of A in my integral, okay? So I go from this equation to this equation. So all I'm doing is integrating the function, plugging in the upper limit, solving for it, and then subtracting the value of the lower limit to get my answer, okay? So let's do an example there. So if I take the integral of x squared dx, and I want to look at it from, in this case, 1 to 2, okay? So I need to integrate this particular function, right? Well, I know I need to identify n is 2, and my result here is 1 over n plus 1, so 1 over 3, times x to the n plus 1, or x cubed. And now I'm going to look at it from 1 to 2, okay? Now notice what I have here. I do not have that arbitrary constant anymore, okay? Because if I had it for this one, look, I'm going to be subtracting it if it's involved in this one. So we can just go ahead and not worry about that particular arbitrary constant. So algebraically, I'm going to factor out my 1/3, and I'm going to say, all right, how about x cubed? Now this is my b, right? So I'm going to plug that in, minus my a value, which is, my a value here which would actually be the 1 cubed, okay? So I'm going to have 1/3 times 8 minus 1, or I'm going to have 1/3 of 7, or 7/3. Now that's the area. So depending upon the units that you were dealing with, you know, area is going to be square units, right? So that's how that one right there works. Okay? So let's look at a different one. Let's look at, how about, let's integrate e to the 2x, and let's go from 0 to 1 on this example, okay? So what is the result of integrating an exponential function? Well, we know that we're going to take our a value and we're going to put it here, right? So I can simply write my 2 here, and it's always e to whatever that function was, okay? And it's from 0 to 1. So my result would be, I'll factor out the 1/2, and I'll have e to the 2x, x being 1, or e squared, okay, minus e to the 2x, well, x is 0 this time, so anything times 0 is 0, right? So what do I have here? I have 1/2 e squared. What's e to the 0? That's 1. So 1 times 1/2 is minus 1/2. Okay? So the integration doesn't change. It stays the same, and all I'm doing now is I'm plugging in my upper limit into the result of the integration and subtracting the lower limit input into my integration, okay? So if I have different kinds of problems, I can use this approach on things. So remember we talked earlier that marginal cost, that's a derivative, right? So if I need an equation for total cost, all I have to do is integrate that, right? So here we're going to look at an example, and the example is we're given a marginal cost function for a company, okay? So the marginal cost function is equal to 75 over radical x, okay? So x is my number of units, and we're interested in finding the total cost of producing the units that are made from units 100 to 400, okay? Now, when I do something like that, from an algebraic standpoint, I want to go ahead and convert this into something that's more readily fits into my equation, okay? So if I look at that, isn't that truly 75 over x to the 1/2, which I would then convert into 75x to the minus 1/2, okay? So from a setup standpoint, if I integrate the marginal cost function, I should get the cost function, right? Because I'm taking the integral of a derivative, I should go back to my original equation. So the total cost of producing the units 100 through 400 would look like this. From 100 to 400, I'm going to integrate 75x to the minus 1/2 dx, okay? And when I do that, remember I'm going to pass through the 75. I'm going to leave him out here, and I'm going to look at what happens in here. And when I do that, I have to identify my A, right? So it's 1 over this A plus 1, okay? So I've got 1 over 1/2 x to the n plus 1. Well, minus 1/2 plus 1 is going to be 1/2, right? And that is going to be from the units 100 to 400, okay? So when I look at this, I actually have 75 times 2x to the 1/2, 100 to 400, right? So I'm going to pull this 2 out, and I'm going to have 150. Now I just have 150 times the square root of my limits, right? So I can look at this as the square root of 400 minus the square root of 100, okay? So I have 150 times square root of 400 is 20. The square root of 100 is 10. So I have 150 times 10, or 1,500. All right. And this was a cost function, so this is actually $1,500. So when they're producing these units, once they get to unit 100 and they've run their production run up to and including unit 400, they're actually going to have spent $1,500, okay? So that's an application of using these definite integrals, having derived that from the Riemann sum, okay? So what have we learned today? Well, I can take the integral of a function, and then what we're going to be dealing with are rates. I can integrate that function and end up with some result, right? That result being this capital F of x. So if I input the upper limit into that function and then subtract the lower limit of that function, I will have gone in and essentially created almost an infinite number, these little thin slivers of areas underneath my curve, effectively eliminating these little areas right here. So I'm getting the exact area underneath that curve, okay? And so that applies to any kind of rate that we go through and integrate, okay? So that concludes our lesson on definite integrals and calculating area. I'll see you next time.